Hello class, it's Dr. Homepage. I wanted to talk about null and alternative hypothesis for a paired samples t-test. So you might have decided based on your research scenario that your test for your final project is going to be a paired samples t-test. In a paired samples t-test, it usually follows this model of that there's a pre-test or some kind of baseline data collection, and then there's some kind of treatment, and then there's a post-test to see if the treatment had any effect on whatever variable you're trying to measure. So I have a little scenario here that fits that model. In this scenario, we're going to imagine I'm the coach of a high school basketball team, and that we're horrible free throw shooters. And so as the coach, I compile all the free throw shooting percentages for all 12 of my players at the end of the season. I decide it's just god-awful, and so I hire a free throw guru. Yes, these people actually exist in the basketball world. So I hire one of these people to work with my players for 3 days a week after school on their free throw form. And that lasts for a month. I do 12 2-hour practice sessions. And then after the coaching's over, we're going to start our summer league. And so then when summer league, during the summer league, I use that as the post-test, and I compile free throw shooting percentages for all of my players in the summer league. So I'm not going to give you any data here because I just want you to be thinking conceptually what that means. Okay, so in a paired samples t-test, we're looking to see if the post-test score or the post-test scores are different than the pre-test scores. So my research question is, did the free throw guru that I hired actually help my players improve their free throw shooting? That's what I want to know. It's important to draw a distinction between an independent samples t-test and a paired samples t-test because each test is doing two different things, and I think this is one of the things that the textbook doesn't really do a good job of delineating for you in the chapters on hypothesis testing. So I'm going to try to fill the gap here. So with a paired samples t-test, each individual, their score on the post-test is very dependent on their score on the pre-test. So we could imagine, if I had a free throw shooter at 44%, not a very good free throw shooter, he's only not even making half of his free throws, I don't really expect that person to suddenly become like a 95% free throw shooter after my coaching. I'm hoping for some improvement. Maybe he can break 50, maybe he can get up towards 60%. But I'm not really expecting this person to be the best free throw shooter ever after our coaching. So where you start, has a big effect on where you end up. As an aside, I imagine I have a very good free throw shooter, maybe who starts at 85%. There's not a lot of room for improvement. Maybe I can get him up close to 90. But again, where he finishes depends on where he starts. And, how significant that improvement is kind of depends on where you start. So, even if a really good shooter moves from like 85% to like 92%, that's like a really big jump in actual basketball terms. And so that has some weight attached to it, even though, it's only a difference of 7 percentage points. So again, the formulas for these and all the math underlying these paired samples t-test is different than an independent samples t-test. Recall in my example for the independent samples t-test, I was just taking a bunch of tomatoes from one group, a bunch of tomatoes from the other group, comparing the means. I wasn't like measuring the change in each tomato and mapping them out and comparing them. And so this is a little bit of a different animal. And it's important that I emphasize that because it's just a more appropriate t-test for a situation where you're doing a pre-test and a post-test. So it's a different test, even though it still falls under the umbrella of a t-test. So hopefully that makes some sense for you. Again, the main thing I want you to take out of this first part here is that the score on the post-test for each of my players is dependent on the score of the pretest. That those scores are related. And so you often hear paired samples t-test referred to as related samples t-tests or within samples t-tests, because we're looking at the scores within each subject. It's another terminology that you might hear going forward. All right, and so because we're really looking at the difference between each individual participant, our null and alternative hypotheses are going to look a little bit different for a paired samples t-test. So let's get down to it. So the null hypothesis, the no change hypothesis, is that the mean difference between the pre and the post test is going to be 0. And so that would mean that despite all my coaching, my players, went through the practice sessions, and then, I was excited and I measured them in the summer league, but you know what? They all shot the same. There's really no difference in how they're shooting the basketball at the free throw line. I encourage you in this class to write it out. It's great to try the nomenclature, but you'll notice I don't use the Greek letters because it's more important that you say what you mean and you're precise about it. So here I've got the mean difference of shooting percentages between the pre-coach players and the post-coach players will be equal to 0. There's not going to be any change in each of my players' shooting. Let's look at my alternative hypothesis. Here, I would expect the difference scores to be greater than 0. And I would expect it to be in a positive direction. If there's an effect, if there's a change due to my hiring of the shooting coach, I would expect the free throw shooting percentages to be better for each player, or at least most of the players in the summer league. So my hope is that each of them improves by a few percentage points. And so that's reflected that I hope that mean difference score is a positive number, and that would mean that the percentages are getting better on the post-test. I wrote it out here as well, and I encourage you to do the same. The mean difference of shooting percentages between the pre-coach players and the post-coach players will be greater than 0. Let me get my verb tense right here. So the mean difference of shooting percentages between the pre-coach players and the post-coach players will be greater than 0. And so this is going to be a directional hypothesis. That means I'm expecting the effect to be in a certain direction. I'm expecting them to be better. And as you'll see from the textbook, that translates into using a one-tailed test down the line. There's sometimes situations where you would use a non-directional test if you just really don't have any clue whatsoever what the treatment might do. Like I know in our course, right, we have a vignette where they talk about students learning under a scented condition and then like a non-scented condition. That one's a little bit more vague. By and large, most of the time, when you're doing a pre and a post test, you have some idea of what the effect's going to be. You're really just trying to determine if it's going to be enough. However, it does come up sometimes where you have a situation where you want a non-directional hypothesis. So we could imagine here that, let's just say like someone made me hire this shooting coach. Maybe the athletic director stepped in and said, yeah, you're just awful, Coach Chris, and I'm going to hire this coach. And I'm pretty skeptical. I don't really think he's going to do anything. I could potentially do a two-tailed test or a non-directional test. My null hypothesis would simply be, again, the same thing, that the mean difference between the pre-test and the post-test is going to be 0. My alternative could just be that the mean difference is going to be not equal to 0. I don't know if it's going to be greater or less. I don't know if this guy is going to come in and just wreck everyone's shooting form. I don't know if he's going to come in and help. I have no clue what to expect here. So In the case I was a researcher and I just didn't have a clue what to expect, I might do a two-tailed test. And so as I think about, that vignette with the sense, read that vignette, think critically about whether you think the researchers think it's going to help or it's going to hinder learning in that scenario, or if they really don't know. You can set up your hypothesis any way. Even after you have data, you can go back to the drawing board on the hypothesis and do another test with it. Null and alternative hypotheses are just theoretical things. That's why I'm presenting them with no data, because I kind of want people to sit and think about in the abstract what they mean, even though that's kind of annoying, I'll admit, but it's worth doing as an exercise to just sort of think about what this means. I drew another one of my Homer Simpson diagrams somewhere here. Let's see if I can find it. Here we go. I decided to use this one because it's supposed to make these nice automatic curves for you, but it didn't on some of my curves, so I'm a little bummed. But I can still get the point across with my Homer Simpson diagrams. But again, when we think about a null hypothesis and an alternative hypothesis, what we're thinking about is really two theoretical distributions, two theoretical outcomes, And with my shooting percentage question, the first theoretical outcome of no change is that, I've got this distribution of shooting percentages on my team from the season, and they weren't very good, and if there's no change, that distribution of shooting percentages is going to be the same. It's going to have the same mean. They're all the new scores are going to sort of fall into this old distribution about where they did, and it'll be pretty unexciting. Then, theoretically, there's this alternative hypothesis where they actually improve. The mean shooting percentage is a little bit higher, and the scores on the team for shooting percentage sort of fall along this new alternative change distribution. So theoretically, you're still kind of thinking about these two curves in your mind, and the question you're really asking with hypothesis testing is when you finally run all the numbers, you're looking at the means and you're looking at the difference between the means in this case, and you're saying, okay, well, these new scores, did they fall under the old, or are they representing a whole new different group of shooting percentages for this team? Should I just expect more of the same, or is this score significant enough to make me think, oh, these clowns actually got better at their shooting? I put up this other curve here just to kind of help you think conceptually about what we're doing with a difference score. And so, in a pretty, it would be a pretty common thing, that the difference score wasn't very high, It'd be a pretty high likelihood that there's not a whole lot of difference, and I can even mark that in the minute I have left here. So we can imagine a scenario where the difference isn't that much, and that translates to a pretty high likelihood on the curve. So if I've got likelihood on this axis. So it's pretty likely that the difference score is going to be insignificant. But it could be that we get a pretty big difference, right? And that wouldn't have as high as a likelihood. The likelihood of that would be lower. So bigger differences have a lower likelihood. And so when you're doing your paired sample t-test, bigger differences are going to make you think, oh, that's interesting, that's unexpected. And the larger the difference score, the more likely it is that you're going to eventually accept this alternative hypothesis and believe that these clowns actually got better at their free throw shooting. Okay, that's enough for now. Thanks so much for watching, and again, shoot me questions you have on this video going forward.